Good day. Today we will solve problem 4.6. So, a mercury thermometer which has been on a table for some time is registering the room temperature at 75 degrees Fahrenheit. Suddenly, it is placed in a 400 degree Fahrenheit oil bath. The following data are obtained for the response of the thermometer. Give two independent estimates of the thermometer time constant. In order to get two independent estimates of the thermometer time constant, we first need to make an energy balance to our system. So first we make an unsteady state energy balance to our system. So to make an energy balance, we need to find the input rate and the output rate and also the rate of accumulation. So in this case, our input rate is just equal to HA x times x minus y. Our output rate is just equal to 0. Our rate of accumulation is just equal to mc dy over dt. So in this case, H is the heat transfer coefficient, A is the surface area of the bulb, X is the surrounding temperature, Y is the temperature of the mercury, M is the mass of the mercury, C is the heat capacity of heat capacity. So before solving this equation by means of Laplace transform, deviation variables will be introduced in this equation. So prior to change in x, so before our temperature changes, the thermometer is at steady state. So meaning at steady state, dy over dt is just equal to 0. So this term here will just be equal to 0. So this equation will become this equation. So HA times x sub s minus y sub s is just equal to 0. So the subscript s here means that um, the temperatures are at steady state. Notice that if we rearrange this equation, we have y sub s is just equal to x sub s. So this just means that if y sub s is just equal to y sub x sub s, the thermometer reads the true bath temperature. Okay, so subtracting this equation in this equation, we have here this equation. So HA times x minus x sub s minus y sub s is just equal to mc dy over dt. So this equation looks complicated. So um, let's try to simplify this one by letting big X as x minus x sub s and big Y as is equal to y minus y sub s. So upon substitution, we have HA times x minus y is equal to mc dy over dt. If we transfer HA here, or dividing both sides by HA, we have x minus y is equal to mc over HA dy over dt. So let us let tau as mc over HA. So taking the Laplace transform of this equation, we have here x of s minus y of s is just equal to tau s y of s. So I'm rearranging this equation. We have y of s over x of s is just equal to 1 over tau s plus 1. So this term here is our transfer function. So for a step function of magnitude a, we have this equation. X of t is just equal to a u of t. So taking the Laplace transform of that equation, we have x of s is just equal to a over s. So upon substitution, so x of s here is being substituted above, so we get this equation. Y of s just equal to a over s times tau s plus 1. So using partial fraction, we have here this, we transform the previous equation into this equation. So now we need to solve C1 and C2. So solving the values for C1 and C2, we get C1 is equal to A and C2 is just equal to negative A. So we can conclude that y of t is just equal to 0 at t is less than 0. And y of t is just equal to a times 1 minus e to the negative t over tau at t is greater than or equal to 0. So this will be our working equation to solve to have our independent estimates for our tau, since we are given temperature at a specific time t in the problem. So so solving for A here is our magnitude of response. So A is just the upper limit minus the lower limit. So in the data earlier, our upper limit is just 400 and our lower limit is 75. So A here is just 325 degrees Fahrenheit. Okay. Now that we have our value for our magnitude of response, which is 325, we can now substitute our value of A to our working equation. So upon substitution, we have our equation y of t is equal to 325 times 1 minus e to the negative t over tau plus 75. So note that we added 75 degrees Fahrenheit in our working equation, since this is the initial temperature of our thermometer. So our final working equation is this equation. Y of t is just equal to 400 minus 325 e to the negative t over tau. So using this equation, we can solve for tau, since we are given our temperature at a specific time t from the data given below. Hence, solving for tau using the values or data given from the table, we have tau is just equal to 9.647, 11.2, 9.788, 10.9, 9.87, 9.95, and 9.75. So that's all, and hope you learned from our discussion about this problem.